Alright guys, as you can see, I'm not going to be here today. We are leaving for Waco today to go compete in regionals for UIL math. So I will miss all day and I wanted to record today's lesson. First of all, understand that you will have a quiz next time over day 3 and day 4 things, and that's dealing with circles and also parabolas. So make sure that you do review the videos that are on Google Classroom if needed so you can score very, very well on that quiz. And that quiz will be for you next Tuesday. Okay, so we're going to talk about conic sections for the rest of this unit. And we've already talked about circles, okay? And circles are basically referring to this shape here. And today we're going to be talking about parabolas. Okay, the next couple of days we will look at ellipses and then hyperbolas. So if you notice from the picture, I'll highlight in blue, this is the circle right here from this cross section of two cones with this plane. Okay, so this plane, meaning that green plane that you see, if I cross this picture, you'll see that a circle is created. Today's lesson is going to be associated with creating those cross sections of parabolas. Okay, the following days, the next class I see you, we will look at ellipses, and then the last day we will look at where it crosses both cones to create this hyperbola. Okay, so here's a visual to show these cross sections in action. Okay, so notice as the planes go through these pictures, which ones are appearing. So you see the circle, now you see this ellipse, now you see a parabola, and then boom, now you see the hyperbola as it goes through. Okay, and then it just keeps going. You see an ellipse right now. Whenever it's horizontal and it's perfectly symmetric, it's back to that circle. Okay, so that's going to be what we're referring to for the rest of this unit. Okay, I have Mrs. Ware doing a video for you guys to actually show this drawing activity. It is one of the pages that you picked up for notes today, but I want you to do that at home. Okay, I would rather you during class to go closer and faster to the actual notes that I have here for the parabola. Okay, so yes, please do watch this video. I will upload this video and I want you to do this at home. And again, Mrs. Ware has graciously offered to record that video, and I will put that online for you guys. So we're going to start here where the parabola starts. Okay, so the parabola is a locus of points as far as just a group of points or a set of points in a plane equidistant from a fixed point, okay, and a fixed line. So there's a point, there's a line, and a parabola is basically created to show that any point on this parabola is going to be equidistant from this point and equidistant from this line. So a point and a line, we're going to learn what those are called. Well, might as well say it right now. This is the focus, and we call this line the directrix. Okay, so let's go ahead and move on. So the parabola has many forms. You have vertical parabolas, and you have horizontal parabolas. Okay, vertical parabolas are the y is equal to x squared, but because the vertical reflections and whatnot, it could be a positive, which this one would be a positive x squared, or it could be a negative that looks something like this. Okay, so that's this negative, this is the positive. And over here is the same thing. Okay, so you have an x is equal to a y squared that is negative, and x is equal to a positive y squared. Think of it as, if here's the origin, everything to the right is that positive x value, and then over here you would have the origin where everything to the left is going to be this negative x value. Okay, so that is the vertex form as far as what we've been used to, of course, with algebra 2 and whatnot. And we can also write these in parametric form. Okay, now we really wouldn't use these normally because, I mean, you're used to writing it in the standard form, or you'll identify it with the general form. We're used to basically using this parametric form as far as Mrs. Hamilton has mentioned, just for the projectile motion kind of type of problems. Okay, so again, know the parametric forms, but whenever you're writing them out, if you were asked to write them out, you're going to be more held accountable for these and these right here. Okay, So standard working form. Standard working form is very, very similar to what you have over here as far as what we were looking at for our original versions of a parabola. The only difference is now is that we're going to add a couple pieces to it, to where we have horizontal shifts, we have vertical shifts, and we also have vertical stretches or compressions, not just reflections of negatives. Okay, so that A value could be a -5, it could be 1/5, things like that, which would show a stretch or a compression. And then also the H and K could show shifts to the left and right or up and down. So think of transformations there. That's that working form, okay? That's referring to the transformations that you could apply to a basic default x squared or y squared graph. Okay, and last but not least, you have the general form. And the general form is when you don't have any parentheses and everything is all distributed out. And it's really close to what we did with a circle that was in the general form for a circle. Okay? The only difference here is C is equal to 0. So that's saying if C is equal to 0, then it's saying 0 times y squared, it won't have a y squared value to it. Okay? And if A is equal to 0, 0 times x squared, it will not have an x value to it. So basically, here you would have something like y is equal to an x squared of some sort. Okay, so it's going to be a vertical type of parabola. And over here you would have x is equal to some type of y squared component. And that could be plus or minus, where you have a horizontal parabola. Just like we had up here as far as the pictures are concerned. They're kind of matching up with this column, and this picture is matching up with this column here. Okay? Alright, so let's go ahead and keep going. So we have a couple of videos that we'd want to show you as far as what it looks like in reference to this focal point or this focus and this directrix that we were talking about. Notice how the equidistant exists between, like if I chose this point here, it's equidistant from the focus as it is to this directrix. If I chose this point here, this distance is equal to this distance here. And that's what creates this locus of infinite points that could exist, just infinite points, that would show that relationship between that distance from that point to the focus and that point to the directrix. Okay. And then finally we have this Desmos. And this Desmos is pretty cool actually, because you can see of how you can play through, and the focus will change this parabola depending on how far it is from the actual parabola. For instance, and you see the negative flip there, the same thing. Let's say that we stop the focal point about here. What we're saying is that this locus of points, let's pick a point here. We could say that the distance, let's choose red. That the distance from that point, whoops, maybe not. Let's choose red up here. This distance is going to be the same as this distance would be. Straight to the point and straight to the line. Okay, so that's that relationship that exists between any point on the graph. Let's move that a little bit to the left. Actually, let me just move the graph. Any point on the graph to the focal point or focus, and any point to the directrix. Just want to reiterate that and show you with those animations. Alright, so a parabola, again, still is a set of all points equidistant from that fixed point and that fixed line. We now know them. And the distance from a parabola's vertex to the focus or the directrix is called the focal length, and we're going to call that P. Okay, so if I were to go back to this thing here, and I showed you the distance between, we do this in orange, the focal point and the vertex, we're going to call this P. So this distance is called P. And because right now we're choosing the vertex as this point on the graph, kind of like what we did over here with this blue dot, if I were to choose here, then I know that that equidistant to this focus, which is called P, is also the same distance to the directrix. Okay, which in this case looks like it's like negative y is equal to negative 0.75. Just a nice horizontal line at y equals negative 0.75. Okay, so this p-value is also the same there. Okay, so they will be the same as far as equidistant because of the definition of the parabola in itself. So this introduces an equation that we will use a lot. Okay, so 4AP is equal to 1 is this relationship that will help us find what that p-value is. Okay, so let's think about this. Y is equal to x squared. What we did to this is we added an a and then an h and a k. And here's an example. Let's say y is equal to 3x minus 2 squared plus 4. What this is showing is, just so you know, a is this coefficient here that shows that vertical stretch or compression. Okay, but a could be negative, it could be positive, whatever it is, that's what you're going to put there for a. And the p-value is going to be solved basically from this relationship. So you could, if you want, say p is equal to 4 over a. So we would put the 3 here. We'd have p is equal to 1/12%. So on our graph over here, this distance between the point and the vertex that we said was p over here would in fact be, p would be 1/12. If and only if the case scenario as far as my example problem here was true. Okay, so it'd be 1/12. And so on and so forth. We're going to do more examples with that. Okay, so here we go. We're going to first start by identifying the vertex, the focal length, the focal point, and the directrix of this parabola. Okay. So immediately, just like we did that last problem, this right here is going to be my a value, which is a negative 0.1. Okay. So if a is equal to negative 0.1, we're going to use 4AP is equal to 1 as my equation. And some of you can memorize that easily. Mrs. Hamilton gave us a nice idea to memorize this. You can think of it as taking 4 AP classes is one tough year, if you will. Okay, so however you want to memorize that 4 AP is equal to 1, by all means do so. Alright, so we have a is equal to 0.1. So if we plug that in, we'd have 4 times that negative 0.1 times p is equal to 1. So we're going to have negative 0.4, p is equal to 1. And if we were to divide it out, we'd get the focal length, okay? Otherwise, the p is equal to this negative 2.5. Okay, so negative 2.5 is going to be that distance. Okay, now let's look at other parts of this parabola. Okay, so I like to get y by itself so that I would move it over and see this equation like this. And oops, it's going to be a 4. And the reason why I like to do that is because from here I will interpret that the opposite is going to be 3. And that what I see, basically following the rules, is going to be that 4. So to me, the vertex is easily identifiable when the y is all by itself. And just the way we memorized how to do transformations, everything inside parentheses is the opposite. Otherwise, the xy method that we talked about, or everything that's outside the parentheses, you follow the rule. You follow that y value. Remember how we mentioned it before, happy wife, happy life. However you want to memorize it, would give you that 3, 4. So the vertex is at 1, 2, 3, 1, 2, 3, 4, and we would label this 3, 4. Okay, so from this, we're going to carefully show that a distance up and down of a p-value of negative 2.5 is going to show that I'm going to go from this 4, and I'm going to go down this 2.5, if you will. Okay, so if I do, this is going to give me a 3, 1.5. So 3, 1.5 is where my focus, so right here, that's my focus, is going to exist. And notice the jump. The jump that occurred was this negative 2.5 from 4. Okay? And then to get the directrix, we would go the opposite direction. So we're still going to do 2.5, but we're going to go this way, 2.5. So that would give us to 6.5. So there's a line, basically, if you were to count 1, 2, 3, 4, 5, 6, and then 0.5, this is where this directrix is going to go. And that's that y is equal to 6.5. And the reason why we say it's y is equal to is because it is a horizontal line. And the way we're going to draw a directrix, we're just going to dash it and show it just like that. Okay? So the focal point, okay, because that's what we're being asked to find, the focal point F is 1.5. The directrix D is y is equal to 6.5. And the focal length we've already found as P, and that was basically this negative 2.5. And finally, the vertex. Identifying the vertex we just got from the original equation of opposite what's inside the parentheses to get the x value, and exactly what you see on the y value to get the y value of that vertex. Okay, so if we want to write this in general form, all we have to do is now take what we have and distribute it all out and see what we get for a final answer. Okay, so let's go ahead and do that. Alright, so we have negative 0.1 x minus 3 squared plus 4. And remember, general form we're trying to get set equal to 0. So PEMDAS tells us we're going to distribute this binomial first. And we know that this is not x squared minus 9 or x squared plus 9. When it has that multiplicity of 2, we're going to write this down twice and distribute, otherwise known as FOIL this method out. Okay, so let's see what we get. So we have the first, we have the outside, and we have the inside, which would give us x squared minus 6x, because you have a negative 3 and a negative 3. And last but not least, you would multiply the last terms. You get a positive 9. So that distributes that out. We still have this negative 0.1a value, that coefficient that we got from earlier that was given to us. And now we're going to distribute this out to all three terms. So that we have y is equal to negative 0.x squared. And you can put the 1 there if you want. And then you would do plus, because a negative times a negative we know is a positive. So it would be plus 0.6x, and then we have minus 0.9, and then plus 4. So minus 0.9 and plus 4 is the same as, let's put a negative 0.9 and a positive 0.4 together, so that we get a positive 3.1. And last but not least, we're just going to move the y over so that we get everything is equal to 0. So I'm going to subtract the y over, but I'm going to write the y is equal to 0, I'm going to write the equation is equal to 0 by putting 0 on the right side. So we have negative 0.x squared plus 0.6x. We are going to put this minus y, and then we're going to do the plus 3.1. Okay? Because remember, in general form, we have all the x's together, we have all the y's together, and then the constant, so that we have 0 all there by itself. So this right here ends up becoming the simplified general form of this parabola. Alright, let's move on to the next one. Our next example, we are going to write the standard form equation of the following parabolas. Okay, so this standard form, we're going to identify that we need to find a sketch as far as is it y is equal to a positive or negative x squared, or is it a horizontal parabola, which is x is equal to a positive or negative y squared. In this case, you can see that this is opening up horizontally, so it's going to be a form of x is equal to a y squared piece. And now what we're going to do is we can see by this picture, by symmetry, that the vertex is going to occur at 0, 0. Okay? So the vertex occurs at 0, 0. We have a point now that we're going to use this x is equal to a times y squared. And this point we're going to use by putting it actually into our equation. That's our x value. 8 is our y value, which will allow us to solve for a. So let's go ahead and put that in. So we get 3.2 is equal to a times 8 squared, which is 64a is equal to 3.2. So if we divide this out, we can use the calculator. It's going to give us a 0.05 for an a value. Okay, so that means this is going to be x is equal to 0.05 y squared. Or if you wanted to manipulate this around, you could multiply the 0.05 over to the left side. So you would, or not multiply, but divide both sides by 0.05 so that you would get 20x is equal to y squared. Either way, but if we're going to do horizontal, I would prefer you to get the x by itself and write it like that. Okay, so again, how did I get this? I just took this and divided basically both sides by this 0.05. That cancels to a form of 1, and this would become 20x on the left side. But again, this is equivalent, but I would rather you do a horizontal by getting y by itself. Just like I would want you to do a vertical parabola up and down by getting y by itself. So again, x by itself is horizontal, y by itself is vertical. Alright, so this one we have two different things. So over here we had a vertex and a point on the graph. This time we have a vertex and the focal point. So let's get a sketch going on of some sort so we can see what is this going to look like. Okay, so 0, -2 is going to be here, and this is my vertex. And then -1, -2, this is going to be my focus. See, and the focus tells you which way it's going to open. So if this is my vertex and it's opening toward the focus, it almost looks like a light on a flashlight, if you will. Like the light bulb of this flashlight is where that focal point would go, because it would bounce off and it would reflect straight out. It would bounce off and reflect straight out. The light would go this way and it would reflect straight out. Hence, that's the reason why we use parabolas for the shape, to maximize the light in a flashlight. Okay? So this tells me where it's opening up. So I know it's a form of x is equal to y squared. In this case, it's going to be a form of x is equal to a -y squared, from what we did at the very beginning of this video. Okay? So let's look at our standard form for this. We have x is equal to a y minus k squared, and we're going to have the plus h. Okay? So again, hk is my vertex. Okay, so h is that x value of 0, and k is that -2 value for my y. So remember, this was 0, -2 as far as my vertex is concerned. Okay, so where am I going to put these values? Well, 0 is going to go here with h. This -2 is going to go where k is at, which will make this look like y plus 2. Because again, everything in parentheses is the opposite. And we don't have to put anything for h because it's 0, and then we have the x here. So if we go back to trying to find the focal length, let me make a little bit of room. We're going to say that for AP classes is one tough year. We can see from this that we have the p-value. We might have to calculate in our brain just a little bit, but the p-value is that distance between the light bulb per se and the vertex. That focus and the vertex. So if the focus is at -1, -2, then that horizontal jump is going to be that 1 value. Okay, so we're going to put a -1 for p. So it'll be 4a times this -1 is equal to 1. Okay, so we have -4a is equal to 1, and we have a is equal to -1/4. So a is showing you that up here on this equation, Let me highlight it in orange. Right here, this A, we're now going to put this negative 1/4. And this negative 1/4 makes sense because it's a horizontal that's reflected so that it's facing to the left. So x is equal to a negative 1/4 x plus 2 squared. And you can write this as far as your equation goes. Because again, it is a horizontal parabola, and I would rather you put it where x is all by itself. Alright, so let's make some room. Let's do this last one. We're going to do a quick sketch, and the sketch is going to show that the vertex is -3, -1. And now this dashed line of the directrix is y is equal to -3/4 is going to show that not at 1, but a -3/4 is where this, oops, I did that wrong. That was x equals -3/4. We want y is -3/4. So not quite -1, but about 75% of that, we have the directrix. So remember, between the directrix and between the focal point is where we're going to have our vertex. So we had that over here, where we had the directrix was here. Oops. We had the focal point here, and in between is where we got this vertex. We know that in between is the vertex, we have the focus, and then we have the directrix. Of course, with this being the same distance here. So let's go back over here. So we have the vertex, we have the directrix. So from here, we're going to show that it's going to shine away from this. So I might have led you to believe that that was a focal point. Just corrected myself if I did. This point right here is the vertex. So on that graph, we're looking at this right here. Okay? So basically, this distance between the directrix and the focus the directrix and the vertex has to double so that we can reach the flashlight over here, the actual bulb, that focal point that we've been talking about. Okay? So that focus is here, that vertex is here, and then the directrix, of course, is this line. So again, one more time. The vertex is always between the focus and the directrix. Okay, so if we're at y is equal to -3/4, then what is this jump that exists between the vertex that was given and this line that was given? Is going to be that small little 1/4 piece, if you will. Okay, so that small little 1/4 piece, we're going to say, is going to be that p-value. So p is -1/4. So if we have 4AP is equal to 1, we'll have 4A, this -1/4 that we saw from the sketch, we are now able to calculate that A value. So we have -1/4 times 4. We see those 4's cancel to a form of 1, and we have -A is equal to 1. So that A is equal to -1. Okay? So this is a vertical, so up or down, this is a vertical parabola, which we learned at the beginning of this video, will take on this standard form right here. We've just calculated A, so we can say it's a -1, which makes sense because it looks like a vertical reflection of some kind across the x-axis. And now we're just going to use our vertex, wherever it was at, to, which is right here, -3, -1, to fill in H and K. So, in parentheses, I'm not going to put this -3, I'm going to put the opposite interpretation, and this -1 is going to see just as you see it. Okay, and that's that x, y, 5 method that we've discussed. And sure enough, if you want to move this 1 over, you could show that this too is the equation of this parabola. But again, the reason why I don't want to show this is because of the x, y, 5 method we've learned. This will show a negative x value, which is opposite in parentheses. But if you look at this over here, it may mislead you to put a +1 there when it's not the case. So the reason why I want people to use this method is that you can use that extension from transformations that we learned this year, you just have to remember y has got to be by itself. Otherwise, even though there's no parentheses over here, you would have to interpret the opposite if you wrote it in this form. So I would hope that you would not write it in this form, that you could just algebraically manipulate it from here and understand how to draw it, how to write it, and how to find all the points important on the parabola. Okay, so let's do the next examples. Number 5, write these equations, or write the equation for the parabola in standard form. Okay, so you can identify already that we are given general form on both of these. We have x, and then we have y squareds. So this is going to be a form of a horizontal, either left or right, parabola. And this one over here has just one y, but it has two x's that we're going to complete the square with. So it'll give us this kind of form, which is going to be a vertical up or down. So let's go ahead and complete the square. Remember, first step is setting it equal to the constant all by itself, and we get negative 139 by moving it over. And now we're just going to group all of our y's together, and we're going to group all of our x's together. Okay, so now that we have them separate and we have them grouped, we want to complete the square. Now, with completing the square, it's easiest to change the coefficient of your square term to 1. So we're going to GCF out this 2 so that we have this left over. And then it'll be plus x is equal to a negative 139. Okay? Remember, completing the square is b over 2 squared. And this is, of course, from that standard quadratic form that we've been used to since Algebra 2. Okay? So the b is the coefficient of that non-squared piece. So in this case, our b value is going to be negative 16. So we take negative 16, we divide it by 2, and when we square it, no matter what, it's going to become a positive. So 8 squared will be a plus 64, and this is what we're going to add right here in parentheses. Now, this is different than what we've done before, because this right here, let's use a triangle for distinguishing that this right here is the change of that coefficient of y squared. So remember how I said what you do to one side you're going to do to the other? You're not going to necessarily add 64 over here. Because of this coefficient of 2 that would multiply through, like distribute to all three of these terms, you're actually going to add over here 128. So it's 2 times 64 to add it to the other side. Okay? Now let's factor this down. So we take the square root of y squared, take the square root of 64. This is our squared piece, and we're going to borrow this sign right here. Whatever that first sign is right here, we're going to borrow and put it in there. So then we get plus x is equal to whatever 139 or negative 139 plus 128 is, which actually is a negative 11. Okay, so we have this as of right now. So now what I want to do is I want to just get x by itself and make sure it's horizontal. So I can say I'm going to subtract this piece over the equal sign so that I have a negative y minus 8 squared. And then we're going to have this minus 11 over here. We just have to make sure that when we complete the square, that I almost forgot to put, that this coefficient that we GCF'd out also goes through. So it's going to be a negative 2 times y minus 8 squared minus the 11, and this would be my standard form for the parabola. So we changed it from general, we completed the square to standard, and all the while, any of those coefficients, remembering that they're going to go through and not be included inside the parentheses. Okay? Alright, so let's do number 6. First step we're going to do is we're going to move this 13 over by having a negative 13 on the right side. We're going to group our x's together. And then we're going to group our y's together. Next thing I notice immediately is that my coefficient is not 1. So I'm going to GCF out that 4. Notice how I GCF'd it out from both. And I'm going to leave a little bit of space to complete that square here. Okay, so let's write everything else. Minus 12y is equal to negative 13. Next, I'm going to identify what is my b value left over. My b value coefficient, again, from this ax squared plus bx plus c standard form for a quadratic is going to be 1. So we have b squared, or sorry, b over 2, which is 1 over 2, and we're going to square it. So this becomes 1/4. So we're adding 1/4 here. But total-wise, we are adding 4 times 1/4, which is like adding 1 to this left side of this equal sign. So what we just did is we added 1 to the left side, well, we now have to add 1 to the other side. What you do to one side, you must do to the other. Okay, so let's bring this down. We take the square root. We take the square root, which would be 1/2. We borrow this first sign, and we make it the squared. And not forgetting, we bring our coefficient down so that we have 4 times the quantity x plus 1/2 squared. Okay? Now, we identified that this was going to be a vertical parabola, so we want to get y by itself. And we know that this is going to give us a negative 12. So what I'm going to do is I'm going to move this over by adding it to the other side. And I'm going to move this over by adding it to this side. So now I have all of this that I'm almost done. I just need to get y all by itself. So I can divide everything by 12. So y is equal to, so let's divide this by 12. Let's divide this by 12. So the 4 and the 12 reduce to 1/3. So you can put 1/3 x plus 1/2 squared plus 1 is, because when you divide by 12, you finally got y all by itself, and you would have this as your final answer. Okay? So if you wanted to see this transformation-wise, kind of like full circle, if you will, you could see that the x value is going to be a negative 1/2. So let's do that. So here's negative 1. We could see about here's the x value, and the y value would be 1. So there would be your vertex. It does have a positive coefficient, so we know it's going to open up. This 1/3 shows that it was a vertical compression of some sort, so it was a little bit wider than the original, if you will. And then that's just the standard form. That's from this form, you're able to draw it out from the vertex and see what it would look like generally as far as transformations are concerned. All right. Now let's do our last example, which is a real-world problem. It says a flashlight has a reflective parabolic mirror that helps project the light out from the bulb. And this is what I was talking about earlier. Notice that the rays are just going to go and bounce straight out, and it's going to maximize all the light that's going to be coming out so that no light escapes and is over here. It's more directional to in front of you of what you actually want to see. And what maximizes that is the parabola shape itself. Okay, so enough of that. So it has a reflective parabolic mirror that mirrors or that helps project the light out from the bulb. This parabolic mirror measures 50 millimeters across and is 15 millimeters deep. Okay? For maximum light output, the bulb should be placed at the focus, like we talked about before, of this parabola. So if we place the bulb a little bit too far from the vertex or a little bit too close, it doesn't maximize that light. So putting it right where the focal point is would maximize that light that comes out. Okay? So we're going to determine the focal distance P, and let me highlight that in blue. P is that distance between the vertex and the focal point. We're going to find that distance at which the light bulb should be placed from the vertex. Hint, write an equation of the parabola based on ordered pairs. Okay, so let's first start off. The vertex, we're going to draw the vertex kind of representative of being at the origin, if you will. So there's the origin. So the vertex is the origin. Okay, we're going to say 0, 0. And we're trying to write the equation based off of ordered pairs. Well, so far I have a 0, 0, which is on the graph, the vertex itself. And then let's pick another point. We could pick this point that was given to us from these dimensions. That if I were to go 25 over to the right, which was half of this 50, and then go 15 meters up, I could create a point that would be 25, 15. So this is on the graph. It's on the parabola. And this one is on the graph, but it specifically is the vertex. Okay, so what we're going to do is, we know it's a vertical parabola. Let's go ahead and get our basic setup started. And we're going to use this point that is on the graph, but not the vertex, right here for the x, and right here for the y. So that we have 15 is equal to a times 25, and then we're going to square. Okay? Again, you want to use a non-vertex point when you're doing it this way so that you can solve for that a value. Because if I use the vertex, a is going to be 0, and that's not the correct answer. So again, one more time, you have to use something that is not the vertex, that is still on the graph, in this for y equals ax squared to solve for a. So 25 squared gives you 625, then you have 15, a times 625. If I divide both sides by 625, you could get a from the calculator is equal to 0.024. So that's that value there. So if a is equal to 0.024, we can now move over to 4AP is equal to 1. So 4 times 0.024 times p is equal to 1. And remember, we're trying to find p. We're trying to determine that focal distance from the vertex. Okay? So multiplying this out and dividing both sides by whatever this equals. So what is this? 0.0, so 1689. So p, so 0.096 is going to be multiplied with p and equal 1, so that when we divide by 0.096, p is going to be 10.24, and in this case, millimeters. So we are going to say 10.24 millimeters from the vertex. That's the distance that's going to be here. From the vertex to where the light bulb should go will be 10.24 millimeters. All right. Make sure that you do the homework. Now that you have all the tools you need to complete the homework on WebAssign, remember that that is due next class that I see you, and it's due by midnight, but you want to have a good majority of it done because we have a quiz over this stuff that you just saw and circles from day 3 the next time I see you, which is next Tuesday. You guys have an awesome weekend.